So, you've probably seen the headlines flying around about Google's new quantum processor. It's called Willow, and it's posting some numbers that are just absolutely staggering. But what's the real story here, behind all the hype? Okay, let's get into it.
Right. This is the number that just stopped everybody in their tracks. Google's Willow chip did a specific task in about 5 minutes. Now get this. To do that same thing, our most powerful supercomputers today would need an estimated 10 to the 25th power years. That's a billion million years. Just try to wrap your head around that. It's a completely incomprehensible amount of time.
So here's the big question, right? Does a number that huge mean your laptop is about to become a paperweight? Are we really on the edge of a full-blown quantum revolution? Well, that's exactly what we're going to unpack here, separating the wild spectacle from the actual science.
First up, let's take a closer look at that headline-grabbing claim and figure out what's really going on under the hood.
You know, what's really fascinating here is that the 5-minute calculation, as impressive as it sounds, actually isn't the most important part of this story. Not even close. The real breakthrough with the Willow chip is all about a fundamental engineering achievement, one that takes on the single biggest roadblock in all of quantum computing.
To really get what Google pulled off, we first have to talk about the core challenge that every single quantum computer is up against, the unbelievable fragility of the quantum world.
Okay, so everything in this world starts with the qubit. Think of it as the quantum version of a classical bit, you know, the ones and zeros that run all the tech we use today. But the qubit has this kind of superpower called superposition, and it means it can be a 0, a 1, or, and this is the weird part, it can exist as both at the very same time. And this is a great way to picture the difference. A classical bit, it's just a light switch. It's either on or it's off. Simple. A qubit, though, is more like a dimmer switch. It can be all the way on, all the way off, or it can exist in this whole spectrum of possibilities in between. Now, this is what gives quantum computers their absolutely immense potential power. But, as you can imagine, that power comes with a pretty steep price. And that price is fragility. I mean, the quantum state of a qubit is so delicate. The tiniest little disturbance, a tiny shift in temperature, a little bit of background noise, even a stray radio wave, can just completely wipe out the information it's holding. We're talking about a lifespan that's measured in microseconds. It's basically the kryptonite of quantum computing. So how in the world do you build a computer with components that are this unstable? Well, the strategy is something called quantum error correction. The basic idea is to bundle a whole group of these fragile physical qubits together to create one single, much more stable and reliable logical qubit that can actually protect the information from all those errors. And that brings us right back to Willow's big moment. This is exactly where Google's new chip represents a massive leap forward in solving that very fragility problem. So here's what the team at Google did. They tested this error correction idea at bigger and bigger scales. They built a logical qubit from a 3x3 grid of physical qubits, then they scaled it up to a 5x5, and finally a 7x7 grid. And the result was just incredible. As the system got bigger, the error rate of that logical qubit actually went down. More physical parts led to a more stable system. And this is the real headline. You have to understand, before this, adding more qubits usually just meant adding more ways for things to go wrong, making the whole system less stable. This experiment is the very first time anyone has proven, in practice, that the theory of scalable quantum error correction actually works. It's a genuinely historic milestone.
But, okay, as exciting as all that is, we gotta put it in context. Let's get real for a second. What does this achievement actually mean for computing right now?
So, remember that incredible 10 to the 25th power year calculation? Well, it was done using a benchmark test. It's called random circuit sampling. This isn't a task that solves a real-world problem, like developing a new medicine or cracking a code. It's a very specific, standardized test that's designed for one thing: to prove that a quantum computer can do something a classical computer just can't. It's a proof of concept, not a practical application. This slide really lays it all out, plain and simple. What Willow proves is that the basic approach to error correction can actually scale, which is a huge win. It shows that the technical path they're on is a good one. But what it is not is a machine that's ready for general computing. It can't run useful programs yet, it definitely can't break encryption, and it is nowhere near the finish line. To even get to that finish line, we're going to need a lot more firepower. I mean, a lot more. Current estimates suggest we'll need quantum computers with thousands, maybe even millions, of these stable, error-corrected logical qubits before they can start to tackle useful problems. So yeah, we're still in the very early days.
So you might be thinking, okay, if we're still so far away, why does this one breakthrough with the Willow chip matter so much for the future? Because it's a foundation stone. It's not simple. Before you can even think about building a skyscraper, you have to prove you can make concrete that's strong enough to hold it up. Willow has basically just proven that the concrete for quantum computing, this idea of scalable error correction, is actually viable. It shows that the #1 requirement for building useful, large-scale quantum machines is truly possible. And once those big machines are built on top of this foundation, wow. They could completely revolutionize fields like material science. We're talking about designing new drugs and batteries atom by atom. They could supercharge AI models and totally change the game for cryptography and secure communications. The potential is just immense.
So in the end, I think this quote just says it all. This is the best way to think about Google's Willow chip. The journey to real practical quantum computing is still going to be long, and it's going to be incredibly hard. But for the very first time, thanks to this engineering breakthrough, that destination is no longer just some theory on a whiteboard. We can actually see the path ahead.